Welcome everyone. My name is Maciej Wojtowicz. Today I'm honored to talk about ASIC versus FPGA selection criteria, compatibility and porting challenges. Have fun. Introduction actually matches the prospect. Probably many of you are familiar with it. So basically the idea of the talk is to start with simple things, then going deeper into details. So hopefully our journey will be useful and interesting for both experienced engineers and some hobbyists or digital hardware enthusiasts that are going to learn a little bit of basics of all hardware designing journey. So let's start with the question from the very beginning. I'm new to hardware digital design and how to start. Well, first I recommend studying just fundamentals of digital design techniques. I listed 3 of them that are great to start with and study. These are logic gates, flip-flops, and state machines. If you are not graduated from some university in electronics or similar fields, you can still find some useful materials for free in internet, or just look for some literature about the theory. And if you are motivated, you could relatively quickly grasp the basics. Then, when the theory is ahead, you can study one of the hardware description languages that are from one side similar to programming languages because they represent the code, but the difference is that programming language in most cases works sequentially, but hardware description languages' goals are just to map the logical design you are going to represent by the textual description. So basically, by writing code in either Verilog or VHDL, your goal is to describe the design that will be progressed by implementation or synthesis tool to make some real digital design out of it. Okay, so let's assume you know the theory. Based on this, you represented some design, and then you want to check if this is going to work. Without stimulating inputs and observing outputs of your design, you will not be able to check it. So you need to use some simulation environment. You can look in the internet for some open source simulation. Some of them exist and can be downloaded by free. Good choices could be Verilator or Icarus. Probably there are more open source, but those 2 I am aware of and confirm that work, I think, well enough to start with. Of course, you can also use some commercial simulators. The most popular one are from Cadence, Mentor, and Synopsys. I know that the problem with the commercial simulators for the beginners can be a price, but you can, if you are motivated and reach proper people or maybe universities, you should be able to get some trial licenses and use it for practicing. So putting all these pieces together, you are able to develop your design, observe internal signals, and iteratively fix issues one by one. But there is another question. Wait a minute. This is all simulation. I cannot take just shown on the photo. Yeah, it means that for people like tangible things, so for them simulation becomes faster or later not enough. Our goal is to get our design in real hardware. So the next step for us is to select appropriate chip architecture. The two essential ones are ASIC and FPGA technologies. Maybe there are more of them, but these two are by far most popular. So the basic difference here is that FPGA is really great for iterative work, mainly because reprogramming is simple and really fast, particularly for small designs. In ASIC, hardware reprogramming is complicated and mostly unreasonable. Why is that? Yeah, because the reprogramming is not the goal of the ASIC. Of course, you can do in ASIC wherever you want, but the goal is to get just a dedicated design for your design purpose. You are able to indirectly reprogram some logic resources. This is possible, or even make FPGA compatible design in ASIC, but in really most use cases this is overkill and better to use FPGA for this purpose. Another worth mentioning things about the FPGA versus ASIC is that you can get FPGA board on demand from any vendors that offer boards on the market. So for the beginners, for the hobbyists, and just for practice, this is just good to look at the offers in the internet and find FPGA board or board suitable for your budget. And with the resources in which your design will be able to be correctly implemented. It is not possible to get an ASIC somewhere in the market because simply speaking, ASIC is going to represent your own design, assuming nobody created your design before, because this is you. You cannot get the ASIC. So as this statement goes, the cost of the ASIC will drastically outperform cost of a single FPGA platform, because FPGA platforms are already manufactured and on sale. To get ASIC manufacture, you need to make an order to the factory, which of course is going to be very costly. So continuing our journey, I think that I convinced you that now we need to focus on implementing our design in FPGA platform. And the most popular companies offering different FPGA boards are Xilinx or Intel. Of course, if you are again smart, you can reach some universities trying to find out if they have some board to lend, and maybe you can use for the practicing real FPGA boards shared with other students. Okay, so we have a knowledge about the design. We implemented our design in hardware description language, successfully simulated it, and now we are going to put it into our FPGA board. So apart from the hardware description language design, we also need one more file, the file with constraints. The constraint file can be very important, particularly for the projects in which power performance area balance is very important, and we want implementation tool to infer optimal design. We can help it to define some timings requirements for critical paths or some clocks or many more other things that is going to help the design to implement faster and better one. Of course, we can also use some other design setup files, like for example DFT setups and low power file, but for simple design these are optional, and HDR design and constraints should be enough in most cases when simple designs are being considered. So we are continuing practicing here, while FPGA tool translates the design, it is going to generate the set of output files. One of the most important one is bit file. This bit file is going to be injected into the FPGA board, and the goal of it is to make connections between FPGA cells. They are logic equivalent to description of your design. But then the beginners can be surprised, because design while working in simulation may not work in FPGA. Even before implementation is complete, you can see a critical error that's going to interrupt the implementation, saying that you could have used some construction in your hardware description language that is not synthesizable. In this case, you need to fix this construction in your hardware description language, and please remember that most simulation tools allow for you to write some constructs that some implementation tools will not accept. But after fixing the issue, we achieved another milestone in our journey. We get our design present in real hardware, that is FPGA. But now we have the same problem as we had for the simulation in the first place, because okay, our design exists in real hardware, but it cannot be controlled and observed, as we don't stimulate its inputs and observe outputs yet. So we need to do this in hardware too, of course. So there are, I think, simple ways of doing so and complex ways. The ways that are simple and the ways that are complex, this classification, I think, depends mainly on the engineering point of view. But I think that for simple ways of stimulating inputs, we can list using some on-board switches. I mean some physical buttons by that the user can change, and these buttons are connected in the FPGA board with the I/O pads of the FPGA chip, and you can control inputs of your design based on these switches. The disadvantage of switches is that manual controlling is very slow, so this is a good way of controlling inputs mainly in very simple designs or only some dedicated nodes timing critical inputs. You can also implement a simple synthesizable input generator apart from your main design that is going to work as another piece of hardware. And the goal of this generator will be to provide cycle after cycle some pattern that is going to go into inputs of your design. And that way we have two synthesizable blocks out of which the one works as a driver and your DUT works as a receiver. And then when these patterns are being provided, you can observe how your outputs are going to react on it. I think that the best way in the group of simple ways is to use virtual drivers based on JTAG. The implementation tools provided along with FPGA board, I mean proprietary tools like Intel Quartus or Vivado Xilinx, allows you from the software side to define some patterns, and you can select some design block in your FPGA system that will be connected with the JTAG interface. So the flow will be like from the PC and tool perspective, you define some probes, some input patterns that go from the software through JTAG interface to the board, to this block, and the block is going to be connected with your design. So this way you have a power to control your design from your computer. That is good. And as you can see here, you can define the probe parameters and source parameters, allowing you to flexibly set the length of the pattern and number of inputs you want to control. As for simple ways of observing outputs, we can list some standard visualization techniques like using diodes, 7-segment displays, LCD graphical displays that are usually already present on FPGA boards. You can also take advantage of gold pins being connected to FPGA outputs, and to these gold pins you can connect some oscilloscope or logic analyzer. The advantage of oscilloscope and logic analyzer comparing with the first three listed items is that you can observe the signals on time domain, but the limitation is that you may not, in the oscilloscope or logic analyzer, you may not have enough separated channels to observe. So if you want to observe hundreds of signals at the same time, you will not likely be able to use oscilloscope effectively. So to achieve that, also the FPGA vendors provide some pieces of software like ChipScope or Signal Tap that automatically drag out some internal signals into the output of your design and uses other FPGA resources to connect all the signals to some visualization part of the software, and the values of these signals in time can go through the JTAG interface, this time from FPGA board into the software, and in this way you can debug your design effectively, similarly as you could do it in normal simulation. Of course, for complex design, you are not able to observe all the internal signals, so this is reasonable to select just some groups being useful for debugging issues in FPGA. Okay, how about the complex way of stimulating inputs and observing outputs? I asked the question, are they really complex? In practice, the professional FPGA designs are not standalone implemented in FPGA platform. You can build a microprocessor or DMA based system, and maybe it sounds scary for the beginners, but the good news is that such systems are possible to be built automatically by FPGA tools. So after playing a little bit with FPGA tools, you should be able to get real multi-peripheral microprocessor-based system in your FPGA with your design included, and controlling can be done like via any microprocessor system, via Linux drivers written in C or standalone drivers written in C. So let's assume you have the transaction layer between hardware and software, and have some Linux embedded system in your FPGA working with this microprocessor. So you can write the bash scripts translating to C, or tests directly in C, in which you can control inputs of your design via simple variables, and also read some status and outputs of your design from the level of C code. This can be very interesting. Okay, so we've achieved another milestone. My design works well in FPGA, and I feel that I can go mass production with it. So when we achieve this level of experience, we are starting to be more and more interested in evaluating ASIC, because in general we must remember that logic resources and routing in FPGA are fixed. That means that for high congested designs, we can have problem with routing and with timing for some specific design areas. In ASIC, there is no redundant cells and no predefined routing, so we have far wider flexibility in determining the critical path. Another advantage of ASIC is that the team can decide in which technology the chip can be manufactured, and when technology is selected, the tool chain, I mean ASIC tool chain, is able to finally generate GDSII file that, simply speaking, includes the chip layout information and all the data needed to manufacture the chip, and then this file is sent to the manufacturer working on the target technology, and your ASIC can be manufactured there. The important thing to know is that the shuttle slot is usually by a few months. Shuttle slots mean the time which the manufacturers can implement your chip. It doesn't happen daily. in general, you must wait a few months between shuttles. So for example, if you plan the shuttle for some day and then the manufacturer just started implementing it, and few days later you find some critical bug, unfortunately you cannot fix it. You need to wait another few months for next shuttle, and this few months can be really costly and can mean end of life for the small company. This is not the problem with FPGA, because in FPGA you can reprogram all the time the connections between the logic resources. So to summarize, if you are aiming to produce the design, getting the performance not achievable by FPGA, and demand for your products justifies mass production of the chips, you should go with ASIC. Good summary of the cost is that single FPGA cost is really much lower than single ASIC cost. It never happens that you reach the manufacturing company to manufacture only one ASIC. This is not profitable for them. So ASIC designs must go mass production. But when you imagine the thousands of chips that you could buy from FPGA company versus thousands of ASICs, this cost, of course, of FPGAs will be higher. So for mass production designs, there is better PPA, but of course higher risk. The risk I explained here, the risk of monthly respins. In FPGA, there is no risk of respins because you are able to reprogram at any time after the bug is fixed. So the question arises how to minimize the risk of ASIC silicon respins and business field issues. Of course, the verification standards must be very high to minimize this risk. Ideally, you should look for the modern verification techniques with the computing power better and better with the time. Some randomized test techniques allows you to run multiple parallel randomized regression. So that allows you to hunt many bugs at simulation time. So this is good to build the team of experts doing this verification, being able to exercise your design very comprehensively. Also, one more important testing environment is gate level simulation. This means simulation not with your HDL description design, but with discrete gates that inferred from your HDL description. To get these gates, you need some ASIC implementation tool and technology library on which you want to synthesize your design with. The library is provided by technology manufacturer, and all the cells contain some physical characteristics and timing characteristics, allowing you to simulate equivalent design that will be manufactured in real factory. But there may still be not enough. And third point I think is very interesting. because in ASIC, in verification of ASIC design, FPGA can still play an important role in prototyping. Think about this. We start ASIC projects and have 2 years for it for first shuttle. So first 2 years are for development. So apart from verifying with those 2 techniques in the very beginning for iteratively changing the design and getting new features, we can implement some initial versions with not all the features implemented in FPGA and just make sure that it is working in real hardware. Of course, we may not be able to achieve the performance we target for ASIC in FPGA, but from my experience, many bugs that couldn't be found in simulations were found in FPGA prototyping. So there is another question then. Does FPGA mass production make sense at all? I would say yes, because if design is really complicated and the price of this design on the market is relatively high, but the design is so unique that there are many customers for this, the risk of ASIC respin, even using all the techniques described in previous slide, is justified because the company cannot afford any failure, because the possible losses from it will outperform the additional cost of having multiple FPGA boards. So yes, that might make sense, particularly when the maximum frequency that design is targeted at is acceptable in FPGA. Remember that even mentioning that in general ASICs can go faster than FPGAs. FPGAs can still work really fast. That will be enough in most use cases. So let's focus a little bit more about FPGA prototyping in ASIC designs. In simple designs, the HDL description in ASIC and its implementation in ASIC and FPGA may match. There is no need to replace any block, but there are some more specific design parts, particularly in high-speed PHY designs, that cannot be directly mapped between ASIC and FPGA. So wanting to prototype some high-speed PHY design targeted in ASIC in FPGA, some changes are needed to reasonably do that. One of the challenge is replacing delay lines. Delay lines for ASIC are very can be implemented very flexibly, can be hardened in fixed places on the chip. The length between all delay elements in lines can be very similar to each other. The routing between each element can be very similar, but for long lines it is literally not possible to any FPGAs to be composed of so many delay elements with regular routing between them. There are also problems with delaying gated clocks versus continuous clocks. In ASIC, you can use just some smart designs to do so. In FPGA, the locking time of board-specific delay lines is relatively long. So for gated clocks, for delaying gated clocks that require locking of the line, anytime they start to be generated, they get resynchronized with continuous clock being delayed every cycle. So in this case, for prototyping, some alternatives needs to be considered, and delay lines are going to be treated as black boxes. One solution is just to use I/O delays that, of course, in practice limits our resolution of the phase shift in line and flexibility. Also, there is an enable pulse for activation of some FPGA specific delay lines. We can use continuous clock to detect when the gated clock is generated. So when the phases are in line there, you can generate using NAND gates some enable signals for that line, allowing you to reduce the problem with the locking of the line for gated clocks. Another problem is general problem with the clock gating. This is very important to write clock gating cells in separated hierarchy in your HDL code. This way you will be the physical design team for both ASIC and FPGA will be able to easily determine the cell to be replaced. For ASIC, this is the smaller problem. Standard clock gating cells composed of the latch and AND gates could be enough, but for FPGA, not only logic structure is important, but also some location of the cells, characteristics. So replacing clock gators can be a little bit of challenge for prototyping. Another consideration area is the option to replace asynchronous resets that are probably to be implemented in original ASIC designs into synchronous ones. In most FPGA platforms, this is possible for the tool to do it automatically. The need for doing this is that you can drastically improve the routing, releasing some routing resources to connect more important, more timing critical paths in your design. So you improve routing, but unfortunately, by changing the reset architecture, your design is no longer logically equivalent. In FPGA, there is more challenging to meet timings for double edge flops, meaning half clock paths. In ASIC, the resources and locations possible for the flops are far more flexible in FPGAs, and from our experience in prototyping FPGAs, of prototyping PHYs, ASIC PHYs in FPGAs, we have had problems with timings for half cycle paths, and some additional dedicated constraints were required to improve those timings. The prototyping is also very good for CDC verification because CDC problems are hard to find in simulations, even if we use some dedicated sync flop modules with randomized delay window. And the problem is that even the most sophisticated cases with randomized clock relationships, we need many hours to simulate milliseconds or even seconds. In FPGA, 1 second is 1 second. So when we use clock signal generators that change frequencies all the time and run many hours those tests, we will get the many hours of different clock relationships, and that we need less time to find some possible metastability issues in FPGA verification. Returning back to writing tests in C, the good thing is that for the ASIC verification and FPGA verification, we can build real system transaction layer and use the same piece of software to verify the ASIC in simulation and FPGA in FPGA. Of course, some parameters in our C environment can be FPGA board specific, but this is possible to port the tests, and with one software driver we can verify our design both in FPGA and in functional simulation. Okay, that's all for today. Thank all for participation and happy hackathon!